Okay, welcome to um, the next week, and this is going to be on chapter 7. This is week number 8, chapter 9, on safety. Okay, so today we're going to go over some of these topics about keeping yourself safe when you're around a station and setting up your own station. So talking about we're going to talk about working safely with electricity. Also making sure you're grounded, that's part of it, and managing radio frequency radiation, being safe around antenna towers and the exposure, and also talking about installing your own antenna tower. I've never done it. I have my license, but I guess they want you to understand the basic concepts. So, first of all, as I reviewed this chapter towards the end, there's a little section in there that says a lot of these things don't necessarily apply to mobile units. Well, radio frequency is radio frequency, but if all you're going to do is use something like this, you don't have to worry so much about all these technical details of interference and electrical safety, because it's pretty much turned on, push and talk. There's not much risk of getting shocked or that sort of thing. But these are all good, important concepts to learn if you do want to go and install a mobile unit in, say, your vehicle, or you want to do one at home. There's some basic things that will help you be safe. So first of all, some of these are really basic, like what happens if you touch electricity and current goes through you, okay? That's like the first thing. What happens? Well, large currents can cause burns in your body. You can get burned. And then there's a table here on 9-2, which shows you what can happen at various current levels. Okay? Table 9-1 on page 9.2 has the different currents and what can happen. Okay? So let's go over a couple of these. First of all, avoiding electrical hazards. So what is the safety hazard of a 12-volt storage battery? So 12-volt storage battery is something like you might find in your car when you're trying to wire up a power connection to your radio if you want to put in a vehicle. So they recommend, obviously, you don't have any metal objects around, because if you short out a battery, it can cause sparks, burns, a lot of that sort of thing. So you just want to keep also jewelry, if you have any jewelry or, bracelets or something like that. You don't want to be leaning over near a battery and then have it short out a battery and connect a current through you or something like that. Even rings apparently can be RF energy. You can actually heat up a ring sometimes when you're talking about antennas. But for the 12-volt storage battery, the safety hazards are things like burns, shocks, fire, and possibly death. Okay? So I'm going to go over this next question, and then we'll come back to the safety hazards of current. Okay? The next question is, what hazards exist in a power supply immediately after turning it off? So a power supply, you turn it on, and it's going to energize. Electricity's going to flow through it. It's going to go from AC to DC, and your radios, a lot of them are DC. Okay, direct current versus alternating current. So you turn it off, and you might think, oh, there's no electricity, even if you unplug it. Well, the hazard is there could be a capacitor in there, and a capacitor is like a battery. And if you were to open it up, which I wouldn't recommend, but if you're opening it up and tinkering with it, you need to know that capacitors can still store energy, and they can shock you. So that's the hazard, is capacitors, and they can store energy for quite a long time. And I'll give you a personal story. I first learned this when I was high school, junior high, I think. Back in the old days when TVs were CRT, cathode ray tubes, before LCDs, they would just take an electron beam and it would go back and forth over the TV a bunch of times and form the picture. Well, it has a tube, and it also had capacitors to store energy. We had this old black and white TV, and we were swapping it out for a color one. And so we had this, or maybe it was an old color one. Anyway, we were moving it because we'd finally got a new one and we'd upgraded. And we had taken the console part off, like the back of it, and we were moving it. And I was helping move it out of the house. And I accidentally touched the back of the tube, and I got shocked. And the thing had been unplugged for a year. And I had no idea that electricity could be stored in there for a year. So it is real. Those capacitors can store, depending on what type it is, but it can store electricity for quite some time. So just be careful around any kind of equipment if you're opening things up. So they actually have what's called a grounding stick, where you just ground it and short it out and discharge it. So they call it a grounding stick to shunt the charge to ground. So, all right. So now let's talk about the risks of current. So higher current is more electricity flowing through you or around you or near you. So 1 milliamp, generally below 1 milliamp, you might touch something, you might not even feel it. 1 milliamp, you might feel a faint little tingling, okay? Very small amount of electricity. 5 milliamps, you can feel a slight shock, okay? Not very painful, but disturbing. The average person can let go, okay? Strong involuntary reactions can lead to other injuries. 6 to 25 milliamps for women and 90 to 30 for men. Apparently there's differences in the amount of voltage that men and women can absorb, and apparently men can absorb more than women, and but it says that can result in a painful shock, loss of muscular control, freezing current, or can't let go. So you may have heard the stories. I've never seen it. I hope I never see it, where someone actually touches, say, an electric fence or something like a wire, and they touch it, and when they grab, the muscles contract, and you can't let go of it, and so you end up staying there, and you're shocked, and it can be a big problem. So that can happen as low as 6 to 25 milliamps for women and 9 to 30 for men. And I don't think any of these are test questions, but it's good safety hazards to know about. 50 to 150 milliamps, extreme pain, respiratory arrest, severe muscular contractions, death is possible. So definitely something you don't want to experience, right? 1,000 to 4,300 milliamps, rhythmic pumping action of the heart ceases, muscular contraction and nerve damage occur, death likely. 10,000 milliamps, cardiac arrest, severe burns, death probable. Okay, so if you think about this, 10,000 milliamps is 10 amps. That current in your house, like your outlet that you plug into like your vacuum or whatever in your wall in your home, those currents can be anywhere from 15 to 20 amps. So that's talking 10,000, that's talking 15,000 to 20,000 milliamps. And so if you look there, it says 10,000 milliamps, or 10 amps can kill you. So that's why we have lots of safety devices in our homes. Like we have a circuit breaker. We also have what's called GFCI, ground fault current interrupter. So that if you were around, it's actually building code in most places. If your outlet is near a source of water, like a bathtub or a sink or something, then they require GFCI, so that if you were to plug something in like a hairdryer and drop it into the bathtub accidentally and you're in the bathtub, it'll trip quicker than it will stop your heart. So it actually depends on how quick that current can be shut off is whether or not you're going to die. So with the GFCI, it will prevent it from happening really quickly and has a really strong spring to actually break that circuit very quickly. So it is very serious and very, you want to be careful around electricity. So now you think about a 12-volt car battery, okay? You may think 12 volts, but guess what? Those batteries have 300 to 400 to 600 cold cranking amps. So you think about 300 amps, that's 300,000 milliamps, and only takes 10,000 to kill you. So a battery in your car has a lot of current that it can easily kill you if you don't know what you're doing. So just be very careful around high voltage and high amps. Actually, it doesn't take a lot of voltage to kill you. It's the amps, the current, that can kill you, as we just went over. So other advices they say in here, like remove excessive jewelry. Don't put your hands around something where the jewelry might, like let's say you're working on a battery and you got like a ring or something, and you accidentally touch the ring to the electrical conductor. If you have a metal conducting ring, you can get shocked that way. Jewelry, anything like that. Also, avoid working alone. If you're working with electricity, it's best to have someone near you with something like an insulator. I remember I always used to hear a broom, like a wooden broom. If somebody's attached to something, you can like touch them with the broom because it's not a conductor, and you can like pull them off of it without you having to have the same thing they're doing. Also, this is kind of funny. Remember, electricity moves a lot faster than you do. Even your briefest touch is pretty long, plenty long enough for electricity to flow. So, doesn't matter if it's AC or DC, they both can burn and kill you if you're not carefully. And they say your body is mostly internal salty water, and so if it gets to you or in you, it can cause problems. So the other thing is to make sure that you're grounded. So like if you're wearing rubber shoes or something, you're grounded. Also, one tip they give you is if you're working with your two hands, put one hand in your pocket. So if you actually touch something, you're not going to have to touch it from one to the other. Because if electricity goes from one side to the other, then it passes through your heart, and then you got a problem. So you want to avoid the electricity going from anywhere along your body, top to bottom, or through your heart, or anything like that, from one leg to the other, from one arm to the other. That's where it becomes very dangerous. And that can create heat, which causes burns and shock and problems. So let's go to 9-4. Okay, now we're going to talk a little bit about the grounding safety for AC current. So for your household type of current, this is on 9-4. They have a little diagram here with 3 colors that you need to know. The first one is green. Green is always ground. So just think green equals ground. Green, the ground always wants to go to Mother Earth. Okay, ground always goes to the earth. So that's an easy one to remember. And in AC in the US, there's white and there's black. Okay, so it's black and white. The white is neutral and the black is what's called hot. Sometimes black can also be red. So that is a question. It says in the United States, what circuit does black wire indicate? In a 3-wire 120 volt cable, black is the hot. That's all you need to know. Black is hot. What is a good way to guard against shock at your station? Well, make sure you have good grounding wire. Make sure you, if you're not sure if a circuit is active, use a tester and test it before you touch it. Make sure that there's no electricity, that it's not energized, and also use things like GFCI circuits, ground fault interrupters. The third question on page 9-4 is, where should a fuse or circuit breaker be installed in a 120 volt AC power circuit? So this one, the answer is in series with a hot conductor. So if you had like, let's say you got this cord here going from one end to the other, and your circuit breaker might be this little black thing in the middle. So if you were to break it or open it, then the current's not going to go from one end to the other. So series is right in line. So a circuit breaker or a fuse needs to be in series with the hot or the black, because the hot is the one that carries electricity. Let's see. Also, make sure you have properly sized wires. So the thicker the wire, the more electricity it can carry, and the thinner the wire, the less electricity it can carry. So if you have a very thin wire, like this one, and you were to try to put like 10 amps through it, it's going to heat up and it might actually just burn or fry and create a fire. So you want to get something bigger, maybe not quite this big. This is a audio-visual cable, but you get the idea. The difference between the thick and the thin. So if this was copper, this would carry more than this. So thicker wire is more current, and it's kind of reverse of what you might think. The lower the number on the gauge, the thicker the wire, and the higher the number, the thinner the wire. So there's a table 9.2 on page 9.4, which shows you the current, the gauge. It's called AWG. G stands for the gauge. I'm not sure what AW is, like American wiring gauge or something. So for example, a 6-gauge wire can carry 55 amps, but you don't want to put a 55 amp circuit on it. You want it to break before it reaches its maximum capacity. So you subtract about 5 amps from that, and they say the maximum breaker you should put is 50 on a 55 amp current. For the 8-gauge wire, okay, it's 40. You can put a maximum of 40, 10-gauge 30, 12-gauge 20, and 14-gauge 15. So in the US, most common, you'll see the 15 or the 20 amp circuits inside your house. So those are typically a 12-gauge wire for the 20 amp circuit for the larger circuit, and then a 14-gauge wire for the smaller circuit of 15 amps. So you can go 20 and 25 amps, but you want to go 5 amps less than that for the breaker because you want it to break before it overheats. So that way you have a little bit of a margin of safety. Let's see. Also, if you have a plug electrical outlet that has 3 wires, there's 2, and then the bottom one is a ground, which connects to the green. So you always want to use the 3-prong if you have it. There's also what's called polarization. This is not in the test, but the GFCI only works if you put the plug in this direction versus that direction, and one blade is thicker than the other, and the one that's thicker goes in the right direction. If you have it in the right direction, then it can do GFCI. So like a hair dryer will have a GFCI blade on it, and you plug it in the right direction, and that means that if you were to drop it in water, it would short out before it would kill you. So GFCI is good. Try not to use adapters to short circuit the GFCI or to get around it, because you're actually just making yourself less safe. If you're trying to do like a GFCI plug to a non-GFCI plug adapter, those do exist, then you can create problems for yourself. Same thing with grounding. You can take a 3-prong outlet and turn it into a 2-prong with an adapter, but then you're losing the grounding safety. So it's not a wise thing to do. So, and also they say never replace a circuit breaker with a fuse larger than you're supposed to. So let's say you have a 20 amp circuit, don't replace it with a 30 amp circuit, because that means it'll take 30 amps of current before it will blow. And if your wire only handles 25, it's going to create a fire before the fuse would blow, and that creates a safety hazard. So never increase your circuit breaker size when replacing. You can go less if you want, but never go more. And if you have an outlet, don't plug like 10 things into one outlet or lots of current, like say your hair dryer and an electrical heater and 2 or 3 more appliances all at the same time. You're going to overload it and heat it up, and it can create a safety hazard. Okay, so the next thing is lightning protection. On 9-5, there's a couple questions here on lightning protection. So you all know the story of Benjamin Franklin. He flew a kite, and the lightning hit the kite, and what happened? The lightning traveled down the string and to a key on a doorknob, and he was like, all right, this is how I'm harnessing electricity. So lightning is real. It can create problems. So there's what's called a lightning arrestor, and the question is, where should it be installed in a coaxial feed line? So let's say you have a coaxial cable going out from your, let's say in your home where your radio is, and it goes out on the roof and up. Where would you put the lightning arrestor? You'd put it right outside your home to a grounding rod before it goes in your home. That way the lightning is not going to travel through your home and into your circuits and create problems inside your home. It's going to go right in the ground before it even goes into your home. So the answer is you put it where it should be installed, where it enters the house, to a ground wire. Okay. What should be done to all external ground rods or earth connections? They should be bonded with heavy, thick wire. So you bonded meaning like welded or bolted or strapped or attached somehow with heavy, thick wire. So the thicker the wire, the more electricity it can handle. And with lightning, there's a lot of electricity, so you want to make sure you have a nice thick wire. And follow all local and building codes. And if you're ever in doubt, consult or hire an electrician to do it right, because that's one thing you don't want to cut corners on, is safety. Next question. Which is the following is a good practice when installing ground wires on a tower for lightning protection? Well, at the base, you want to attach a large wire to the ground. So let's say you got a tower with like a square tower thing going up, like you would see radio antennas or something. Every leg of the tower should have a lightning or a ground rod into it, and it should be attached securely with a large wire or a grounding rod. So next question, which of the following is true when installing a grounding conductor used for lightning protection? So if you are doing one of these yourself, or you're watching an electrician do it, the good practice is make sure it's as short as possible. The shorter the distance to the ground, the less chance the electricity will have to jump or create problems or a spark or anything. Also, they say to avoid bends in the wire. So if you got a big wire like this and you have a bend, the lightning could kind of like jump off or something like that. It can have a risk of sparking off. So you want it to be as straight as you can when you're installing wiring for a lightning rod. Next question. Which of the following establishes grounding requirements for an amateur radio antenna? So it's local building codes or electrical codes. So those consult your electrical codes, building codes, for the requirements on radio towers or antennas. All right. Also, it has a little note in here at the bottom of 9.5. Lightning jumps across switches quite easily. Physically unplug the power cable during a thunderstorm or there's a lot of lightning possibilities. They even recommend unplugging it. You can't just turn off a switch because let's say you got your computer and it's plugged into the wall, but you've turned off your computer. Well, that's great, but if lightning hits and goes into the circuit, it's going to go through that computer because the switch has maybe a little tiny distance between it to keep electricity away, where if you unplug it, it's like feet. That it's not going to jump feet. Likely not, depending on the lightning bolt and where it is, but unplugging your devices is a good idea. And then, attach them to a power strip or something. So you only have to unplug one thing instead of unplugging the 10 things that you plug your power strip into. Well, maybe not 10, maybe 3 or 4, but on 9-6, managing RF. So radio frequency in your station, or radio RFI, RF radiation, radio frequency radiation. Which of the following conductors is preferred for bonding at RF? So when you're attaching something to RF, you want short, solid, heavy wire. So that's what you want to prefer. Conductor, something thick. There's some examples they give here, like a copper pipe, heavy wire, or an actual sheet of flashing, like a metal copper sheet. And so they have an example here. On 9-2, they have a little figure here that shows you how you would bond or connect. So basically the idea here is you connect all of your equipment to one common ground. So whether it's an outlet or an actual strip of a pipe or thick wire, here in this diagram they show attaching this bonding common ground of your transmitter, your radio, your computer, your keyer for like CW if you're doing Morse code, and maybe an antenna switch, and you connect all those to the same ground. And the reason you do that is because you want to prevent unequal voltages across different appliances. So let's say you had your computer plugged into one thing and your transceiver into another, there might be an unequal voltage which can create noise. And noise can create interference, and that interference can be picked up as distorted audio or garbled signals. So the question here is, what is a symptom of RF feedback in a transmitter or transceiver? It's distorted audio. So if you were to pick up your radio and push a button and transmit, and you hear a nearby computer speaker or TV speaker that starts to go bzzz, or raises a hum or something like that, it's interference, and you're picking up the radiation from this antenna transmitting across, and the speaker can actually pick it up, or the electronic device. So one symptom of it is distorted audio. And I'll talk about how to eliminate that in just a moment, which is the next section, a 9-7, RFI interference. Okay, so I've got some examples here. Oh, they have some examples here of how to eliminate interference. Okay, so what happens is, let's say I'm transmitting over here on this radio and I have a nearby wire and I'm transmitting. Well, there's energy going from this antenna, even though you can't see it, and the wire might pick up bits of this energy. And what that will do is cause a distortion or interference. And so what you do is you put what's called an RF choke. And this particular one is a Yaesu adapter for a 12-volt cigarette lighter in your car. And at the end where you plug the radio into, I plug the radio into it, you'll notice there's this little round barrel-looking thing. That's called an RF choke. And they actually loop it a couple times through it. They do a couple loops and put it through here. And it's ferrite, which is some kind of iron. And what it does is it absorbs it and stops it here from being transmitted either direction. So you also see these on monitors. Like this is an HDMI computer monitor cable. And you notice both ends, they have these little barrels. Well, it's the same thing. If you don't have this and you're transmitting, the radio waves can pick up the cable and then cause static or interference on your TV screen. So it picks it up here and it stops it at this choke and absorbs the energy. So you can put these chokes, in this case they have it on both ends, so it's preventing it from going out from your computer and into the monitor and vice versa. So they've got them on both ends. So those are called filters. There's high pass and low pass filters. Also, it's important if you are trying to prevent a certain frequency that you know like what type of filter it is based on the frequency you're trying to prevent. So here's the question. Which of the following could you use to cure distorted audio caused by RF current on the shield of a microphone cable? So let's say this was my microphone, even though it's an adapter. If I'm talking as my microphone and I'm getting feedback or something, you could put an RF choke on the wire to prevent interference and distorted audio. So it'll prevent it from being received or transmitted. There's also power line filters that you can put on electricity where you plug it in that will help prevent these signals going in and out of your equipment via the neutral or hot connectors of your AC power. So there's low pass and high pass band filters that you can install on antenna feed lines. So they have an example here of a cordless phone. So cordless phone charger, same kind of thing. It might pick up some interference and then cause problems with your circuit. So they put little filters there as well. You can put them on your television, on your transmitter, and or your antenna. So on the next page, 9-8, they have a picture of a few of these. They can be round toroids like a donut shape. They can be a cylinder, or they can even be square. And I guess you can make your own. I've never done it, but you can put a donut and just wrap your own wire through it, a donut-shaped iron core. So they're known as RF chokes. Which of the following can cause radio frequency interference? So the answer here is fundamental overload, harmonics, and spurious emissions. So basically, if I'm really close to a wire like this, I'm transmitting really close, you're going to get emissions really close. So the further you away, the less strong the signal is. It's weaker the further you go, and the closer, the stronger the signal. So distance is one thing. Also, the frequency at which you're transmitting can determine the harmonics, which is where the interference can come in. Okay, fundamental overload. That's just like putting too much power around something. So I'll give you an example. I had a 50-watt VHF radio that I was testing. I'm putting in my car. And I had the antenna, and I put it inside my house, and I just had like a cookie sheet and a magnetic mount, so it just sticks to the cookie sheet, the metal's cookie sheet. And I turned it on full 50-watt power, and I did a transmission, and all of a sudden, I hear my smoke alarm go beep, 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 and I let go, and it quits beeping. And I'm like, ooh, that's interesting. It only takes 50 watts of RFI from that antenna to actually have the smoke alarm pick up that RFI and cause interference. And it actually triggered the smoke alarm little beeps on the electronics. So you can, electronics in your house, if you're doing like 25, 50 watts or 100 or something like that, they can pick up stuff if you're not careful about where things are going, like your antenna and how close it is to your other electronics. So that's overload. It's just a lot of power going out of your antenna can be picked up by devices. Okay, so here's another question. This has to do with if you happen to live near an AM or FM broadcast station. So near a radio tower, if you live near one, what would cause a radio to receive amateur radio transmissions unintentionally? It's basically high overload. So you might have an AM radio that looks like this, and suddenly it's in a similar frequency, and you might start picking up stuff. I never experienced it, but apparently it's possible. So if you have overload, strong signals really near, how can overload on non-amateur radio or TV receiver be reduced or eliminated? That is with filters, like a high-pass, low-pass filter, something like this. You can eliminate your TV from picking up these signals by putting on filters, okay? And T7B07, which of the following can reduce overload of a VHF transceiver by a nearby commercial station? There's a broadcast reject filter, apparently, they call it. It's just some subtype of filter. So if you live near a TV or radio station, you might get filters on your devices so that it will reject those specific signals. So it depends on the frequency they're transmitting and so on. You have to tell them, all right, this radio station, and I know the frequency of the VHF or the AM or the FM, what it is, you tell them, and then apparently you can purchase filters designed for certain frequencies. Okay, next one, 9-9, next page. Spurious emissions, leakage, and harmonics. Harmonics is like the frequency when you're oscillating at the same frequency of something that's on the other end, like a transmitter or receiver. What should be the first step to resolve non-fiber optic cable TV interference caused by your radio station? Okay, so let's say you live really close, maybe in an apartment or close next door to somebody, and you start transmitting, and then they come over and say, hey, I'm getting these weird things, and I think your radio is causing it. I see a tower outside. Maybe your tower is causing problems to my device. Well, there's some FCC rules we'll go over about that, about who has to fix what and whose responsibility it is to fix it. But what should be the first step? And notice they say non-fiber optic. Fiber optic is light, so your radio is not going to cause problems if you have a fiber internet or fiber cable or something. You know, you can say, look, that's fiber. It has nothing to do with RFI. That's light. It's not electricity and radio waves, so it's not my problem. So they are specifically targeting, you know, cable or coaxial or something that has conductors. So the first thing you should do is check for faulty connections. So if you had a coaxial cable and there's a faulty connection or a loose connection, it can then be open to receive interference. Or if your cable is a break in the line, then it can leak out. The radiation can kind of like go out, just like poking a hole in a garden hose. It can leak out going out. It can also receive coming in if it's, you know, not properly sealed. So also the other thing you could do is install a low pass band filter. So that should be the first thing, is check for connectors and check for any breaks in the line and install a filter. All right, next one, good practices in your station. Which of the following is a reason to use shielded wire? It's to prevent bad RFI radiation. So if it's shielded, the electricity is going to stay on the outside of it and it's not going to go in your signal and create problems. So it's to prevent bad radiation. Now here's the one about the neighbors. Okay. Which of the following actions should you take if a neighbor tells you your station's transmissions are interfering with their radio or TV reception? So there's a whole section here about that. But first of all, they recommend you start at your own home appliances. Make sure that your own home appliances are not being interfered with in your own home. And if they are, if you install a filter, does it resolve the problem? And if it does, you can tell the other person, look, according to FCC rules, if you're operating an unlicensed device, like let's say a toaster or AM radio or something, every piece of electronic equipment this applies to has to have an FCC label on it with a warning. And most people just read the piece of paper and throw it away because they're like, oh, what's this FCC stuff? And they throw it away and they don't look at it. But what it says on there is this device must accept interference, and it has to accept it. So you're the ham radio person next door, you're transmitting, and it accepts the interference, and they get interference. So it's their responsibility to resolve their own receiving equipment. Is that they have to solve it. So you don't have any responsibility to do it. However, as a good neighbor, you can go over and say, look, I've got some ideas for you. You might want to put in a filter, make sure it's grounded, make sure your connections are good. You can do some of those things to be helpful, but it's their responsibility to correct it. Now, likewise, let's say they have a blender, okay, electric blender, or something with a motor that's can cause a lot of radio things to go out, radio frequency, RFI. So they turn on the blender, and when they push it, your TV goes, lots of static. This used to be the case in VHF, UHF TV stations in the old days before everything went digital. My mom would turn on the blender, and while she's blending, the picture would become distorted. As soon as she turns it off, the interference goes away. Well, the same principle might apply with your radio station. You're transmitting, they get interference on their TV, and you let go, and you quit transmitting, and the interference goes away. And then you notice a pattern here, and they're like, wait, I think your station is causing a problem. And you can say, well, look, you're the one that has to solve it. But if they're the one, say with a blender causing interference, then they're required to not interfere with ham radio because you're licensed to operate on that frequency and they're not allowed to interfere on those frequencies. So if they're interfering with your frequency for their blender, they have to fix it. So that is also part of FCC rules that are explained in this chapter. So it's called Part 15 rules, and it's FCC Part 15 on 9-10. They have a whole little description and overview of that. I'll get to that in just a minute, a little bit more. Well, actually, top of 9-10. What should you do if something in your neighbor's home is causing harmful interference? Well, you can kindly explain to them the FCC rules, tell them they can't interfere and they can't transmit on those frequencies as interfering. They're not allowed to cause harmful interference on purpose. You can try to help them and say, look, you need to put a filter on your blender or whatever, so you're not causing my interference. You have to pay for your filter because it's your blender, but here's what you might do, or ground it, or whatever it is. And you can try to help them eliminate harmful radiation, but it's not your obligation. It's their responsibility as the one generating it to make sure they're not generating harmful interference. Apparently, the FCC can get involved if you want, but the first thing they're going to ask you is, what have you done to try to resolve it amicably, nicely, right? So try to be nice and talk to your neighbors if this becomes a problem, but you can't get the FCC involved if the person is not willing to cooperate and they continue to generate interference. And this is the benefit of being licensed. You have the right to transmit on these frequencies and they can't interfere with you. You have some rights on that. So here's what they say. An unlicensed device permitted under Part 15 must accept interference caused by a properly licensed station such as ham radio. So let's say they got a blender or a radio or a TV. Let's say a TV is probably a better example. It's an unlicensed device under Part 15 and they have to accept harmful interference from your station. They need to put a filter on their equipment. So if it's a Part 15 device, which when you buy it, it will tell you, and if you don't know, you can look it up. Look it up by the model and serial number. You can go to the FCC's website. Most of it, I think anything sold in the US has to have an FCC ID on it. So you look up the ID and you can Google that and you can find what the rules are on that specific device if you wanted to know. All right, next one, 9/11, safety. We're going to talk about exposure to RFI. So there's two different types of radiation. There's ionizing and non-ionizing radiation. So ionizing radiation is like what you think of as radioactive stuff, right? Like a nuclear something. Nuclear power plant, for example. Okay. And ionizing radiation is where you have an element like copper or something or whatever it is, and it's the radiation is strong enough to knock the electron off of the atom, which can cause genetic damage. Now, if this happens in your body, you can create problems, right? Typical genetic mutations that we think of when we think about radiation. So ionizing radiation is very concerning, but that's not what we're talking about when we're talking about RFI. RFI is non-ionizing radiation, so it doesn't have that capability. It's not going to damage your genetics. It's not going to knock off electrons on your body or stuff because it's not that strong. But what it can do is cause an electrical current. And as we've talked about at the beginning, inducing a current can create heat, which can cause burns and damage, okay? So RFI, the main risk from that is burns and heat, okay? What type of radiation are radio signals? The first question, they're called non-ionizing radiation. So that's the type, answer to that question. Now there is exposure limits, and they have a table on, I think it's the next page, 912, yeah, we'll get to that in a minute, but they have a table that gives you MPE, maximum permissible exposure limits. So kind of like when you go and get your teeth x-rayed for a doctor's appointment or something, there's a maximum amount of radiation you can be exposed to and still be healthy. Well, it's the same thing with RFI. There's a maximum limit, and it's also a component of time, which is what they call duty cycle. So you could be exposed to a lot of energy at a brief period of time for a millisecond, it's okay. But if you're at several seconds and you're close to it, it can be a problem. So it's a function of time and power, okay? So they also vary with the type of frequency that you're vibrating at. And so your frequency like 400 megahertz versus 150 megahertz. Those frequency ranges the maximum you can be exposed to depends on the frequency. And the reason is because your body is resonant at certain frequencies. Okay. So that's why the question is, why do exposure limits vary with frequency? Well, it's because the absorption of your body varies by frequency also. And there's a kind of a funny note in here. It says on page 912, they have this exposure limits here. And this part, you need to know this part. The biggest part of the frequency that's dangerous for the human body is between 30 megahertz and 1500 megahertz. So in that range is where the human body is resonant. So they say, for example, an adult head is resonant at 400 megahertz. So it depends on the size of the body part and that sort of thing and how close it is. So your head is 400. Apparently smaller parts of your body like fingers might be resonant at lower or higher ranges. But if another thing that's interesting is that your body is resonant at 35 megahertz if the person is grounded and 70 megahertz if you're not grounded. So apparently it can also vary depending on if you're grounded because the electricity can go through you to the ground or not, so it's going to change. So the question on 912, I'm kind of skipping ahead a little bit. At which of the following frequencies does maximum permissible exposure have the lowest values? It's 30 megahertz is the low to 1500. So that's where it's the lowest. And it's 30 to 300 on this particular table. There's what's called controlled and uncontrolled exposure, which I'll go into in just a moment. But back to 911 here, section 911, page 911, it says, what hazard is created by touching an antenna during transmission? So let's say you go up to KSL broadcast station and you're foolish enough to go right next to the tower. What would happen if they're transmitting and you touch it? Well, you can get a burn. It can burn you, okay? Same thing can happen at a lower wattage, like 100, 200, 1500 watts on a ham radio antenna. You don't want to get near it and touch it while it's broadcasting because you can create burns, okay? How does RF radiation differ from ionizing radiation? That's what I was talking about, the radioactivity versus non-radioactive. So RFI is non-radioactive. You can still create burns though. And then the next question, who is responsible for ensuring that no person is exposed to RF energy above the limits? It's the station licensee. So whoever owns and is licensed to operate the station, they're responsible for making sure someone is not getting too close to get burned or creating a problem, okay, above those limits. So when you're operating your station, you have to make sure that people don't get close to it, which is the next topic, which is controlled and uncontrolled exposure limits. So this little table here has between 30 and 1500 is the lowest range because your body's resonant, and the higher and lower frequencies you can have more exposure and it's not as dangerous. So they have what's called power density, so it's a function of the distance and how much electricity is going across your body or in the air at that distance. So a controlled area is like your home. So in your home, you'll notice the controlled exposure limit is a little bit higher than the uncontrolled. So in a controlled area, you assume like you know where the tower is. You shouldn't go out next to your backyard and stand there while someone's talking, you know, or if it's not up high. If it's up high, that's another test question, is you can raise it higher to increase the distance and lessen the exposure. So you don't want to go climb on the tower and say, all right, now transmit, and you're right next to it. It's a controlled environment. You know where it's at. And so you have a pretty high limit. So the idea is that you keep people away from those areas with signs or with, instructions. You figure if you live there and you know what's going on, you're okay. You just stay away from those areas when you're transmitting. Now, if it's uncontrolled, like a neighbor passing by your back fence or something, the exposure limit is less. So you want to, keep your antennas away from the property lines if you can, or in the center of your property line so that it's not impacting neighbors around you. Next section, page 913, duty cycle. Okay, so this has to do with how much time you're exposed to it. So the question is, how does the allowable power density for RF safety change if duty cycle changes from 100 to 50%? So let's take the example of you're transmitting for 2 minutes. That's 100%. You're transmitting all the time for at 100 watts, okay, for 2 minutes. Now, if you're transmitting for 1 minute, during that 2 minutes, if you're only transmitting half of the time, then it's basically 1 minute of exposure instead of 2 minutes of exposure. So 100 watts over 2 minutes might be 200 watts if you add the 100 for 1 minute and 100 for the next minute. But if you're only transmitting half the time over that same 2 minute interval, then it's really 100 minutes, 100 watts, or 1 minute, 100 watts. So it's, the answer is here is it's 2 times higher. You can transmit higher at a 50% than you can at 100%. It's kind of like, how long do you hold the flame next to your hand before you get burned? So if you just pass it really quickly, you're not going to get burned. But if you hold it there for a long period of time, you're going to get burned. So it's the same thing with RF. The longer you hold it and the more you're transmitting, the more likelihood you're going to be exposed to more and get burned. Okay. So, and also like the power would be like the higher the flame or the hotter the flame, right? So the lower the flame, the lower the power, the less the risk of getting burned. But if you hold it right next to you on a low power, you can eventually get burned. So that's why they have the notion of time, and it's called duty cycle. Why is duty cycle one of the factors used to determine safe arc exposure? Well, because it determines the average amount of power or energy that you're going to be exposed to or absorb. What is the definition of the duty cycle? During the averaging time, it's the percentage of the time divided by the total time. So let's say I'm on the air for 2 minutes, but I'm only talking half the time. That's a 50% duty cycle. So it's just percentage of time versus the total time you're talking or using it. They have an averaging period, which it says is 6 minutes for controlled environments and 30 minutes for uncontrolled environments. I don't know if that's a test question. I don't see it on there. It might not be, but just remember that in case that's on there. Next page, 914. Evaluating exposure. So this is, all right, okay, I've got my radio. Since I can't see it, I don't know how much it's putting out. How do I determine if it's dangerous or not? So something like a small 5 watt, it's not that dangerous. You're going to be fine. Mobile units are generally exempt from having to determine if it's dangerous or not. Mobile units, most of them are 5 watts, 8 at the most. Then ones you put in your vehicle might go 50. Some of them go as high as 100. Those are more exempt from some of those regulations. But if you install a home base station like a tower and you've got a room in your house for it, you're going to need to determine exposure levels. So what factors affect the amount of exposure of people near an amateur station? So they have 5 factors listed. Power, so how much you're putting out, which is kind of like the heat of a flame. The mode, which is how you're operating, so it could be, and they have some modes listed later, like Morse code versus voice versus digital versus FM versus AM. They all have different amounts of energy they put out depending on the mode. And then time that you're transmitting and time you're receiving is a factor. And antenna gain, which is the direction your antenna is pointing. So just think of it as, you don't aim the antenna at somebody and then try to send the energy there because you could burn them, right, if they're close. So you don't go towards, so it's the gain is the direction of your antenna. And then the frequency. So the different frequencies are going to put out different amounts. So those are the factors. It's power, mode, time, the direction of your antenna, and the frequency. Those are the things that are going to affect how much you're exposed to something and whether it's dangerous or not. Which of the following is an acceptable method to determine whether your station complies with the exposure regulations? So I think what I understood from this was they have an online ARRL calculator that complies with the FCC standards. So you can go online and determine it. You put in a bunch of factors, those 4 or 5 factors I just mentioned, and it will help you determine if you're over or under the limit, which those factors plus distance of where that person or where things are in relation to the antenna. So how can you make sure your station stays in compliance with safety regulations? So let's say you're doing a 1500 watt station or 200 watt station mobile unit. You do have to evaluate it and make sure that it's fine. Now, if you change the antenna or increase the power, put an amplifier on it, change the mode, change your antenna. Those things are going to cause you to need to reevaluate. So if you want to make sure you're still in compliance, don't change any of those things and you'll know you'll be fine. But when you change certain things, you're required to like reevaluate and make sure it's still safe. Okay. Next one, safety measures. Which of the following actions can reduce exposure to radiation? Well, decrease your power. Go further away from it, away from people or away from where hazards are. You can raise your antenna. If you get it up off the ground, then it's further away from people being exposed. You can point it away from people or where people are, so the direction of your antenna. And also away from property lines. Go further into your property, the less it's going to radiate out towards your neighbors. So those are some things you can do to reduce your exposure. I mean, this is pretty basic. Figure 9.6, they're like, raise your tower, keep away from people, right? So pretty simple. They have a little diagram here showing you the difference between voice over here and then CW or Morse code on the right. You can see the Morse code is like a strong peak for a period of time and then nothing and then another strong beep. It's like deet deet, whereas voice is like up and down. So the Morse code actually has it's a mode where it puts out more power and you're gonna be more exposed than you would if you're using voice. So that's why mode does determine. All right, so over here they have a table of the duty cycle of the different modes, like Morse code versus voice, and they tell you like percentage of time that the signal is on. So conversational single sideband, that's just picking up and talking. Conversationally, you may be only talking 20% of the time or 40% of the time. Now, if you're using AM with no modulation, even though you're pushing the button, it's transmitting it's doing 100% duty cycle. So there's that table there you can look over. Digital, same thing. It's transmitting digital data 100% of the time. So that's your duty cycle that you would commonly use. Next page, mechanical safety. This is the last one, 917. And these ones are kind of common sense, but this will kind of wrap it up. The physical safety, mechanical safety. Okay. Which of the following is an important safety precaution to observe when putting up in a tower? Well, it's the same thing when flying a kite. Avoid the power lines, right? You don't put your antenna near a power line. That's pretty common sense, right? What is the purpose of a safety wire through a turnbuckle used in tension guy lines? So a guy line, let's say you're putting up this tower and you have these like side wires coming out attached to the ground. You've seen them on radio transmitters or antennas, radio stations. Those are called guy wires. They have a turnbuckle that you twist to tighten it. And why do they put a little wire through it? It's to prevent it from spinning and then loosening and the tower can tip, or it's to prevent it from loosening due to vibration or twisting. So that's the purpose of the safety wire through the turnbuckle of those guy lines. What is the minimum safe distance from a power line to allow when installing an antenna? So let's say you got your power line over here and you got your antenna up here. Well, if it falls, it's going to touch the power line and create a problem, right? So you want to go your height plus 50% away. So height plus 50%, and if it falls, it's not going to touch the power line. So it's height, which is the base plus the mast plus 50%. So that if you're close, it's going to touch and create a problem. But if you're far away, 150% distance, it's going to fall and not touch the power line. So that's the safe distance. They recommend that it's at least 10 feet away from wherever it would be if it were to fall down as a margin of error. What is the proper grounding method for a tower? You attach an 8-foot grounding rod for each tower leg and you bond them to each other and to the tower. Bonding meaning connect with something like a metal piece or bolt or wire or weld or something. Why should you avoid attaching an antenna to a utility pole? So you got a power line and you see, oh, well, there's power lines going there. Let's just put my ham radio antenna on top of it. Why would you not want to do that? Well, if some mechanical failure happens, it will contact the power line and zap your radio station and create a problem for electricity in your area. That's common sense too. just because you see a utility pole doesn't mean you can just go climb up there and start putting stuff on it, right? There's laws against that, first of all. Second of all, it's an electrical hazard. So on 918, on figure 9-8, they have the example here of like your antenna falling and touching the power line. So that's listed over there. 8-foot grounding rods for each leg of the tower if you're putting up your own. I've covered that. The last part is the fun part. 919. If you're going climbing and you want to climb the tower, what should you have? Okay, what equipment should you have? I've never done this, but what is required when climbing an antenna tower? There's like 4 things. Climbing harness, something you strap around yourself and attach. Gloves that are electrically rated. They call them tie-off gloves, I guess. A hard hat and some goggles because you want to stay safe, right? So this question's kind of funny. Under what circumstances is it safe to climb a tower without a helper or observer? I think it's never. You don't want to ever get up there without somebody watching you or helping you, so that if there's a problem, you've got someone that can render assistance. Which is the following is an important safety rule to remember when using a crank-up tower. So I got this crank-up tower that you crank, and it just goes up and up and up and up like a gear. And I decide I want to climb on that. What should you do? Well, put like some kind of safety thing so it locks in place and it's not going to go fall down while you're on it, because the weight can make things slip. So you put a safety thing in there, or just simply fully retract it before you start climbing on the part that's above ground. Again, that's sort of common sense in my opinion, but that's the question and the last answer. Thank you for joining me on chapter 9, and good luck with the test.